Suppose we have a thin-shelled sphere of charge. The total charge here is Q. It is a uniform distribution, so my surface charge density, I'm using sigma here. On other videos, I might use the eta, depends on which textbook I happen to be using at the time. I'm more in the sigma camp right now than eta, but if you're looking at some other source and where I'm using eta, this is also used for surface charge density in some places. That is equal to charge over A, so I know that it's equal to my Q over 4 pi r squared if big R is the radius of the circle. But it's also true for it, since it's a uniform distribution, it doesn't really matter which area I take. I can take a small little patch and that ratio stays the same, and so that's also equal to dq over dA. In other words, sigma is equal to this, which we will exploit at the very end, but in an intermediate step, I know that dq is equal to sigma dA. I have another charge, a point charge here, a distance L away, so from here to here is the distance L, and this charge is little q. So I'm going to have big Q and little q. Now, if we were to solve what is the force on this one, there are some shortcuts that we can take, so this is basically deriving a shortcut. I'm going to set up a coordinate axis here. And just so that I'm consistent with my notes, I'm going to make that the x-axis. I'm going to make this the y-axis. And then z would be coming out. And as such, we'll set up our coordinate system with I hat in the x direction, j hat in the y direction, and then in a right-handed coordinate system, k hat would be coming straight out. If you're new to this, in other words, you did not have me for 251, or if you've forgotten, I tend not to use x hat, y hat, z hat, because that seems to fall into the hands of big math. Basically, the math people have sort of brainwashed people to think that x, y, and yes, I indeed have fallen into that as well. But because our coordinate system doesn't have to always be horizontal vertical, I tend to use I hat, j hat, k hat to try to break people out of that a little bit. And so I'm sort of have a foot in both camps at the moment. So what I want to do is I want to figure out what is the force on this little charge q from this big charge q. So what I'm going to do is I need to, if we think about the generic steps, first I need to create a differential dq. And so I'm going to create a differential dq is I'm going to take a ring of charge that is a distance little r from little q. So every point on this ring of charge is the same distance away. If I take a look at this charge right here at this particular point, it's creating a force in that direction right there. Now, we don't know if big Q or little q are positive or negative. Generally, when you're doing something like this, you assume that they're positive. If it's negative, then the math still holds. You just put a minus sign into the math equation and it flips the direction around. And then from this point right here, there's going to be a charge force there'll be a force in that direction. Well, notice the symmetry here, that whatever the force is, that the horizontal components, horizontal as I've written them, the components in the x and z parallel to the xz plane will cancel out. The only force that will remain is the force that is in the y direction. I need a temporary angle here, so I'm going to label that alpha. This angle right here, that angle right there is theta. And so I have a triangle here where this length here is big R, this angle is theta, this angle is alpha, this distance length is little r, and that is L. I might take the point over here in terms of drawing it, so just for those who can't flip around in their head quickly, that's R, theta, alpha, little r, and L. And basically, there's 360 degrees of this because this hoop right here is a circle. So the force at this point from my differential, again, thinking about the generic steps, when I created the differential, so this has some charge dq. I plug into the formula. So I have my temporary angles here, theta and alpha. They will, in the end, go away. The differential of my force is going to be from this position right here is k little q dq over r squared, little r squared, times, well, there are components here. This is alpha. In other words, this angle right here is alpha. And so times the cosine of alpha in the j direction, plus something in the, I hat plus or minus k hat direction. These are the components right here that will cancel out in the end. In math class, we would go through, we'd do the full derivative and show that this part just drops out to 0. We're not going to do that in physics. We have a much quicker way of doing it. It's called proof by symmetry, or argument by symmetry. That argument that for every force in that direction, there's one in the opposite direction. And so these would cancel out. So ultimately, that is going to go away. So my force is going to be in the j hat direction, given the way I've set this up, times kq dq over little r squared cosine alpha. So notice what I've done here is I've pulled my constants out. For some of you, you'll be looking at this k right here and you're going, wait, what is that k? This is Coulomb's constant. For some of you, it might be a little bit more sophisticated, and instead of using k, you do 1 over 4 pi epsilon sub naught, where that's the permittivity of free space. We don't have to, you can use this instead of Coulomb's constant. This is more generic. This actually allows for some greater flexibility later on. However, for the sake of writing, I'm not writing this because I'm writing enough as it is. So I'm just going to keep the k in there. Notice here, I brought the constants out. K is a constant. Little q is a constant. It's some point charge right there. I have 3 variables. Alpha is a variable because alpha depends upon where this big circle is. Little r is a variable because r is the distance from the circle to that point, and that will vary depending upon where I am on the sphere. And dq is a variable because, well, that's my differential. So I need to get these in terms of a single variable. I can first deal with this dq. So this becomes j hat k little q times sigma dA over r squared cosine alpha. Sigma is a constant. That's a unit that I said earlier. This is a uniform distribution, so that will pop out. So this becomes j hat kq sigma dA over r squared cosine alpha. We still have 3 variables, but we can now figure out dA at least a little bit here. That what is the area of this infinitesimally thin little hoop that I've drawn right here? Well, it's a hoop, which means that if I think about if I have a band of anything, so if I have a band of anything here, and this is my incredibly sophisticated drawing of a band, there is a circumference and then there's a thickness to it. This has some radius of, we'll just call it x. Then the circumference is 2 pi x, and then the thickness we'll deal with in just a second. So first off, what is that? Well, that radius of my hoop there is that distance right there. And so I see from this that x is equal to r sine theta. Now, the thickness of the hoop, if I imagine I'm going to take a look at this little section right there. I got my center right here. This angle here is a differential off my angle theta here, because that's my theta right there. So this, since this is infinitesimally thin, this is some infinitesimally small sliver of the angle. I have radius r here, and so this becomes r d theta. Therefore, given all that, I know my area is equal to the circumference, 2 pi times r sine theta, times the thickness, which is r d theta. So this now becomes 2 pi r squared sine theta d theta. And so now, plugging into this equation right here for my dA, I now have my force is in the j hat direction, kq sigma, times the integral of, so j hat kq sigma times the integral of 2 pi big R squared sine theta d theta over little r squared cosine alpha. Pull the constants out, and so I have j hat kq sigma 2 pi big R squared, so 2 pi r squared, all right. Well, that's with sine theta d theta over little r squared cosine alpha. So I've taken my formula here, where I had my 3 variables, changed it around so I have 3 variables, and then I went through some math there, and now I have 3 variables again. Now this actually is a simpler way of dealing with it. This will help us out in just a moment. If we take a look at the triangles over here, I'm going to take a look at this one right here. Redraw it. This was r, theta, L, alpha, and little r. We now are going to use law of cosines. Now, law of cosines, if you have forgotten what law of cosines is, you might want to do just a quick refresher. It's basically the more generic equation for the Pythagorean theorem. So I'm going to use it twice. One, I'm going to solve for little r squared. So little r squared is equal to big R squared plus L squared minus 2 big R L times the cosine of whatever's opposite little r, which is theta. And I'm now going to do one in terms of big R here. So big R squared equals little r squared plus L squared minus 2 little r L, cosine of whatever's opposite big R, which is alpha. And the rest, of course, is obvious. Or if you're not happy to see it at the time, what I'm going to do here is I need to figure out what is cosine theta d theta, and then I'm going to figure out what is cosine alpha. So from this equation, I'm going to get cosine alpha. From this equation, I'm going to get sine theta d theta. However, I have cosine theta, and I need sine theta d theta. So how do you get it? You take a derivative. So I'm going to take the differential of this. So this becomes 2 little r d little r equals, that's a constant, so there is no differential. They do not change at all. And then over here, I'm left with negative 2 big R L, and then the derivative of cosine theta. Well, the derivative of cosine theta is negative sine theta, so those negatives cancel out, and I'm left with sine theta d theta. So now solving for sine theta d theta, the 2's cancel out, and so sine theta d theta is equal to little r d little r over big RL. And so now I can plug into here. And so my force is equal to j hat k q sigma 2 pi big R squared integral of little r d little r over big RL little r squared cosine alpha. The big R and L are constants. That R is going to cancel out with one of those. And so this becomes j hat kq sigma 2 pi big R over L integral of dr over r cosine alpha. Now we can figure out what cosine alpha is from this right here. And if we just solve for cosine alpha, we get cosine alpha is equal to that. So now, if we make that substitution there, so F is equal to j hat kq sigma 2 pi big R over L integral of dr times 1 over r. Now I separated that. It's just for a conceptual thing that we're going to do in just a second, or a math thing we're going to do in just a second. And then cosine of alpha right there. So r squared over 2rl plus L squared minus R squared over 2RL. I separated that into the sum of two fractions here with a common denominator just because of the math thing that's coming up next. There are other ways of approaching it, but I figured it's easier. May as well do it now than later. When I distribute the 1 over R now, we end up with this coefficient times the integral of dr times, well, the r here and the r here will cancel out with that r when I distribute, so I'm left with 1 over 2l plus, and then over here I end up with L squared minus big R squared over 2L little r squared. Notice I have a 1 over 2L here. I'm going to factor that out. And so now I have J hat K Q sigma 2 pi big R squared over 2L squared. The 2L comes out times that gives us the L squared times the integral of dr plus the integral of L squared minus big R squared over little r squared dr. Now I'm keeping this here instead of distributing the coefficient, because that's going to make life a little bit simpler coming up. And so now we need to have limits of integration. Let's bring out the first drawing. So the limits of integration, since little r is my differential, I need to figure out what are the maximum and minimum values. The minimum value of little r is this distance right here, which is just the length, L, minus the radius of the circle. So this would be L minus r. The largest value of little r is when I'm down at this point down here. So that would be the largest value of little r. And that is going to be, well, the L plus the radius of the circle. And so this goes from L plus r, or from L minus r to L plus r, L minus r to L plus r. Now we integrate. So I have this whole thing up front and integrating that. So this becomes, I'm integrating here. So this becomes r from L minus r to L plus r. Plus over here, I have L squared minus big R squared times negative 1 over r from L minus r to L plus r. And so we get this big coefficient up front times L plus r minus L minus r, substituting, plus this right here. I'm going to go ahead and factor this one. This is a difference of perfect squares, so that's L minus r, L plus r, times negative L plus r, 1 over L plus r, minus negative 1 over L minus r. And so over here, L minus L will cancel out, r minus negative r becomes 2r, so this is 2r. Got the coefficient up front. Plus, and now when I distribute this is why I did it, the L plus r's will cancel out, and so I'm left with a negative L minus r. And then distribute over here, the L minus r's cancel out, the two minus signs cancel out, and so what I'm left with is plus L plus r. This right here, negative L and L cancel, negative negative r's, r plus r is 2r. And so I'm left with J hat K Q sigma, the 2's will cancel out, so we'll just do pi big R squared over L squared times 4r. There's obviously a mistake here. That should be r right there, and that should be an r right there. This is not r squared. It just should have been brought straight down. So r. And so this now becomes J hat K Q sigma pi 4r squared. Now the squared is supposed to come in over L squared. Now, has this made our life any better? Well, yes, of course it has. And so if we go back to what sigma equals, remember the uniform charge distribution, sigma was a temporary variable. It was not given in the initial problem, but that's equal to the total charge over the area, surface area of the sphere here. And so this becomes KQ, well, we can do it slightly more sophisticatedly. So from this right here, we have Q is equal to 4 pi r squared sigma. And I just happen to have 4 pi r squared sigma right there, slightly different order. So I get K little q, big Q over L squared, J hat. In other words, the force between these two charges is as if this whole sphere is a point charge, a distance L away, and plugging straight into Coulomb's formula. So when I'm outside something with spherical symmetry right here, I can pretend it is a point charge at the center. And if you recall back to when I was doing the sort of generic steps, that was one of the shortcuts that can be taken. Now there's another derivation that I can do where I assume that L is less than R, than big R right here, if L. So this, the whole derivation here assumed, and that kicked in as soon as I put in my limits here, that if L was greater than big R, but if L is less than big R, and we went through all that, we'd end up with 0. So this is if L is bigger than big R, and then the force would be equal to 0 if L is less than big R. Now, I have not done the derivation here. There is a link to when I did it with the gravitational formula where I did the option where it was equal to 0. And, feel free to peruse that, or you can come back up here. If L is less than R, then if you think about it, I'm inside the circle here. The lowest value of R, let's see if that is L. The smallest value of R is going to be R minus L, and the largest value will be R plus L. The difference is that that flips around, and that ultimately you'll end up with 0 here. And that is the derivation. And now I assume all of you feel just a little bit better about yourselves for having gone through that, because that's what physics is all about. It's making people feel better about themselves.